Hi guys, good morning. I'm back to talk about streams. So we're moving on to chapter 11, getting into water away from the geologic material, the soils and the rocks that we've talked about so far. And so I'm going to record the content from the chapter in two parts. This one is about just kind of some stream basics, water basics, and then the next part is going to be about floods and erosion. So let me share my screen. Share. Sorry, let me go back to the beginning here. Okay. So, first of all, as we get into the discussion of water, it's important to remember that our Earth is very special in the fact that it contains an enormous amount of liquid water. This picture is a famous photograph called the Blue Marble. It was the first full photograph that was taken of the planet Earth by the Apollo missions in 1972. So it was not that long ago that people had actually never seen a picture of the whole Earth before, even though today we're so used to seeing this kind of thing. And it's called the Blue Marble because, of course, it looks primarily blue. You can see Africa and the Arabian Peninsula, but mostly we see a lot of ocean with some clouds. And of course, both the ocean and the clouds are made of water. So we're going to kind of talk about streams right now, but streams actually make up a very small portion of the water that's on our planet. 97% of all the water is found in the oceans, which are these kind of massive reservoirs of the water. And we will talk about oceans in a couple weeks. So of the fresh water that's on our planet, which is the water that's required for terrestrial organisms, right? Organisms that live on the planet, or sorry, on the land part of our planet. Of that component, most of it is found in ice, in glaciers and ice caps in places like Greenland and places like Antarctica. So that's like about 77%. And water that finds itself frozen in those locations often is held up there for long periods of time. Like in some cases, we have ice that's been frozen for almost 1 million years. Sometimes ice can freeze and melt out quickly, but a lot of times it has what's called a long residence time, where it's trapped there and then not really circulating in the atmosphere. The next biggest component is groundwater. About 22% of the water on our planet is in underneath the ground, kind of below the soil in the saturated zone. That's called the groundwater. And also the water that travels down into the soil below the water table into the groundwater, into the aquifers, has a relatively long residence time, meaning it stays there for a long period of time and often is not circulating in the environment. And then all the other forms of water, the lakes, the kind of surface soil moisture, the water in the atmosphere and the clouds and humidity, and rivers and streams that we're going to talk about, and in living organisms, all of those things have very, very small amounts of water. So 0.3% in lakes, 0.003% in rivers. So these are very small fractions, but of course, they're the water that's very kind of accessible to many living organisms. And so as people that live on the planet and as part of ecosystems that exist on the surface of the planet, we're very kind of in tune to these parts of the water. And then also you'll notice that the residence times, the amount of time that the water stays in these kind of smaller reservoirs, is relatively short compared to the amount of time that the water might be trapped in a glacier or in a groundwater aquifer. So some really big lakes might be able to store water for a long period of time, but smaller lakes and all these other things are going to have water kind of come in and then move out over the period of days or weeks or hours in some cases. And so that also makes that water just much more accessible for humans and for other kinds of organisms. So anyway, we call these different places that water might be stored reservoirs. And of course, that doesn't mean that they're like literally a reservoir, kind of a man-made lake to store water, but they're a place where water can exist on the landscape. Okay, so the water moves between these different reservoirs in what's called the water cycle. Hydrologic cycle is kind of a fancy jargony term that just basically means water cycle. And what that means is it's just a model. So a model is something that's kind of a simplified version of something that helps us understand. And so we have a model for how water moves around in the environment. And a pretty simplified model for water is kind of the simple cycle that shows precipitation, the movement of water from the air down to the ground as rain or snow or sleet or hail, and then evaporation, the movement of water from a water form either on the ground in a lake or river, or from the soil surface, or from a plant, from an animal, into the atmosphere. And then condensation, the transformation of water from a vapor phase, from a gas phase back into a water phase to form little tiny water droplets that form things like clouds in the atmosphere. So in this case, as the water is moving around, it's changing phase. So a phase change means moving between like being a liquid or a gas. That's the most kind of important phase. But then of course a phase change could also be like a liquid and a solid. So if you're forming an ice and then the ice is melting, that would be a phase change as well. So as water moves between these reservoirs, it's often experiencing some sort of phase change. Of course, that I just showed you is a very simplified version of the hydrologic or water cycle. This is a more complex version that shows like infiltration of water down into the soil, percolation of water down into deep kind of groundwater surface areas. It shows evaporation, transpiration, which is a kind of evaporative loss from plants, surface flow, groundwater, subsurface flow. And so it shows that that picture that we saw before is a simplified model. It's more simple than what we see in reality. And then of course, this picture, which is even more complicated than the last picture, is also really simplified as well. There's really more kinds of complex interactions that happen with water in the real world than we can hope to ever capture in a diagram like this. But this shows some of the most important both reservoirs, places where water is stored, and then also kind of movements or transportation forms as water moves from one location to another. Okay, so we're going to talk about water for a few weeks, water in the oceans, water in the atmosphere, but first we're going to start with streams and rivers. And again, even though these are very small amounts of water relative to the overall water, this is water that we are very kind of in tune with and we depend on a lot, so it's important for us to understand. So I have a couple questions for you. The first one is, where does the water in rivers come from? And then the second part is, which direction does water move once it gets into the streams and rivers? So I'll give you a moment to think about that a little bit. So to answer the first question, basically water that comes into rivers ultimately comes from the sky. It was in like a gaseous form, and then it condensed into be a cloud, and then it eventually fell down to the ground as precipitation. It flowed across the surface of soil and rock and collected in streams and rivers. And so the surface flow is a big component that ends up getting into streams and rivers. That's water that kind of runs along the surface of the soil and a rock. And then also that some of that precipitation might kind of infiltrate down into the soil and then might flow underground, and then kind of groundwater might actually flow into a stream from the side of the stream as well. And that is sometimes called base flow or groundwater flow. So you've probably observed times where streams or rivers are flowing, even though there hasn't been precipitation for a long period of time, right? It's summertime around here. Maybe we haven't had rain for a couple months. All the snow is melted, so there's not any old precipitation that's still melting into streams. And you might be wondering, like, where is this water coming from? And the answer is base flow. Water that fell as precipitation earlier in the year is kind of drained down and it's been stored in the soil, and then it's kind of seeping from the soil into the river beds. But again, ultimately it can be kind of followed on its path back to precipitation, which is how that water got into the watershed in the first place. Okay, so then the second question, which direction does water move? I think we've all experienced this. At any time we've spilled something, basically water moves downhill. Gravity acts on water and pulls the water down to the lowest possible point. Just like anything else that we drop on the landscape, it's going to end up rolling, or in this case, if it's water, flowing downhill. So waterfalls flow downhill, but any streams or rivers do that as well. Okay, so I just mentioned a term called a watershed, and that might be a term you've heard before, but just to make sure everybody knows what I'm talking about, a watershed is an area that drains to the same point. So basically, if you look at all the hill slopes around you and you imagine if it started to rain on those hill slopes, the water we know runs downhill. And if we follow kind of the downhill path that water would take, and eventually we imagine it would flow into kind of a bigger stream that's probably somewhere in the center of that watershed, then we can kind of look at all the area that rain would have fallen on that would ultimately end up in the stream, and we can call that land area the watershed. And sometimes people refer to these as drainage basins, although sometimes drainage basins have a component of groundwater flow as well, which might be a little bit disconnected from the surface flow, but we're not going to really get into that a lot here. And I also want to acknowledge that you can have watersheds on multiple scales. So I could think about like a small watershed on the Feather River College campus. When it rains on the Feather River College campus, water kind of drains from the hill slopes along kind of the main road to upper campus, and then it kind of drains into that little stream along the side of the road, and then it flows downhill. And so there's a little watershed there, but then that watershed sits in a much bigger watershed that flows into Spanish Creek. And so we can have multiple different watersheds that sit inside other bigger watersheds. So we could call that nested. And then the amount of water that's going to end up flowing in a particular river depends on, first, the size of the watershed. So something like Spanish Creek that has a much bigger watershed than just that tiny little creek that flows along the side of the road in upper campus of Feather River College. It's going to have much more water because it drains a bigger area. And then going farther downstream, the Feather River has a much bigger watershed than Spanish Creek, so it's going to be bigger. The Sacramento River has a bigger drainage, bigger watershed, right? Most of Northern California is draining into the Sacramento River, so it's going to have much greater flow. So the bigger the watershed, the bigger the river. But then also climate has a component. So if you live in an area where you get a lot of rain, then you're going to have more water flowing in your river than if you live in somewhere like Reno, where you get like 7 inches of rain a year. Then you're just going to have less water moving around in the environment. So we have lots of different kinds of watersheds in our state, and we are not going to get a lot into water management in this particular class, but we have a lot of political and social conflict around how we manage our water, who has access to water. And a lot of times this is because we have watersheds that cut across different kinds of political boundaries. So whether that's cuts across different cities or counties or even states or even countries, right? We have water that flows from the US to Canada and Canada to the US and US to Mexico, not to mention in between states, counties, and cities. And so interestingly, before we had our kind of current layout of states, there were some people, including famously Wesley Powell, who was kind of a famous explorer who came out to the Western United States. And he was a Civil War veteran. He was a very interesting guy. He spoke many, many languages. He rafted the Grand Canyon twice without an arm. He lost an arm during the Civil War. I said he spoke many languages. He's here photographed with a famous Native American who is a kind of companion and an adventurer along with him on many of his journeys, named Tao Gu. I'm probably pronouncing that wrong, unfortunately. But anyway, he was a really interesting guy. He made a lot of observations about what was going on in the Western United States, charted a lot of rivers, right, including his adventures rafting some of them. And One thing that he concluded, first of all, was that a lot of the West was not suitable for agriculture. He reported back to the kind of government along the East Coast that he did not think we should be farming in most parts of the southeastern United States or southwestern United States. But also he proposed that as we started to annex this area, that we designed political state boundaries around watersheds, because he knew that the lack of water would lead to political conflicts. And so he said we should organize our political structures around where water goes. So this was a kind of proposed map he made of this kind of what called the arid region of the United States, showing these different drainage regions, and then proposing how these could be kind of different, politically and socially defined areas. Here's another map showing the kind of watershed states of the United States. So if we kind of worked with basically the states that we have now, but tried to kind of rearrange them so that they would kind of be functional within certain watersheds, this is kind of a proposed way that we could do this. So you can kind of see how these states get a little bit funky, but then you can see how they're kind of capturing big portions of watersheds. So anyway, interesting concept. Okay, so there's a few kind of basic terms about streams and rivers that I want to include here, and then the next lecture that I'll record kind of talks about some of the impacts of these stream and river characteristics and behaviors. So first of all, one thing that we measure and communicate a lot about streams is the gradient of the stream. So that's basically like how steep the stream is. So if we think about basically the rise over run, kind of a math concept, like how much vertical distance a stream dropped over how much horizontal distance was covered. So maybe the stream drops 200 feet over a mile. We could kind of divide the vertical distance, the 200 feet, by the mile, which is 5,280 feet. And then I can't do that math in my head off the top of my head, but you could get some sort of stream gradient where you could figure out like the percent slope or the degree slope that was being experienced by the stream. And that's another thing that might impact the speed of the water in the stream. So that brings us to stream velocity, or the speed of the water. And velocity is a term that generally means the speed that something is traveling, but also has a directional component, talks about which direction it's moving. And generally, there's kind of some back of the envelope calculations that say streams move about 1 meter per second. So about 3 feet per second, but that does vary quite a bit depending on how much precipitation is flowing in a stream, the gradient of the slope, and also the place that you sit within the stream can have an impact on how fast the water is moving. And generally the water that's in the middle of the stream, that's far away from the stream banks or the floor of the stream, is going to have the highest velocity. And that's basically because it doesn't experience any friction. The water that is moving past the stream banks or the stream floor is kind of getting a little pushback from the solid pieces of the bank or the floor. That frictional force that's pushing back against the stream slows the water down, creates a little drag on the water. And so usually the fastest speed is out in the middle. And so if you throw like little sticks or something in a stream, you'll see that if you throw one out in the middle, usually that's going to be moving a little bit faster than little sticks that you might be putting right along the edge. And then also if you were down a little bit from the surface where you didn't have any friction from the air, that would actually be the place that was moving fastest of all. Okay, a couple more stream terms. So discharge of a stream, which is also sometimes called the flow or the flow rate of the stream, is different from the velocity of the stream. So the velocity of the stream is just like one particular like molecule or little section of water, how fast, like in feet per second, it's moving, or meters per second it's moving. And discharge or flow is a volumetric rate. So how much volume of water is moving past a particular point on the stream at any given time. So you could have water in a small stream and in a big river that's moving at the same velocity. Maybe they're both moving about 3 feet per second. But if the big river has a lot more water in it, it's going to have a much bigger discharge or flow because a lot more water is passing a certain point on the river at the same time, even if each little water molecule is moving at the same speed. So the way that you can calculate the discharge of the water is by taking the depth of the stream times the width of the stream, which kind of gives you the cross-sectional area of the stream. So basically how big a slice across the river is. And then you multiply that by the speed of the water molecules that are moving past that point. And then that gives you something that has kind of a volumetric, a three-dimensional thing. So if your depth and width and velocity were measured in meters, you could get like a cubic meters per second measurement, or a lot of times this would be measured in feet. So a depth in feet, a width in feet, and then a velocity in feet per second would yield cubic feet per second, or sometimes called CFS, a common unit of stream discharge or stream flow rate. Okay, so there's the basics. We're going to stop there and then I'll record another video.